Calc 12, Chapter 1.3, we're going to look at graphing polynomial functions. We can use our graphing calculators to make some conjectures about higher degree polynomial functions, but you can use my program called Interactive Graphs, or you can go to the website desmos.com. Let's start out by looking at some even degree polynomials. Here we have a quartic and another quartic, but let's look at it in factored form because it's a little bit easier. We have x plus 3, x plus 2, x plus 1, x minus 1. So that's 4 intercepts. Here's another quartic, and let's look at the shape. So these are called valleys and hills. There's 3 valleys and hills here. There's 3 valleys and hills here, and it's a degree 4. So it looks like we have degrees is greater than number of hills and valleys. Okay, let's look at the leading coefficient. How does that affect the shape? Okay, this one's positive, opens up. This one's negative, opens down, just like quadratics. So, the leading coefficient affects concavity, and we have up when it's positive, and down when it's negative, just like quadratics. Let's look at some slightly different quartics. Negative 2x to the 4 and x to the 4 again. However, if we look at it in factored form, we have repeated roots. X plus 2 occurs twice. Here, x minus 2 occurs twice. So at negative 2 and at 2, it touches the x-axis and doesn't cross. Touches the x-axis and doesn't cross. With the other zeros, it crosses. Okay, so it looks like repeated roots have an effect. So 2 repeated roots bounce off. And how would you describe the range? Okay, so let's look at the range here. It starts there and goes down. Here, starts there, goes up. Here, it has starts there and goes up. Here, it starts there and goes down. So how would you describe the range? It has an absolute or global, min or max. So what does this mean? The range is not all reals. Let's look at odd degree polynomials. Degree 3 and degree 5. So cubic and quintic. We have 1, 2, hills and valleys. 1, 2, 3, 4. So again, degree is greater than number of hills and valleys. How does the leading coefficient affect the shape? Okay, so we have positive, and here we have negative. So, very generally, we can say that it matches the slope of a line. Or we can say that for positive, it starts in quadrant 3, ends in quadrant 1. For negative, starts in quadrant 2, ends in quadrant 4. Let's look at a few more. This is a quintic, and we have another quintic. This one has a negative coefficient. So again, it matches the slope of a line. It goes negative. And this one's positive, and it goes upwards. Okay, so again, it matches the slope of the line. Or you could say that this starts in quadrant 2, ends in quadrant 4. Starts in quadrant 3, ends in quadrant 1. Okay, do repeated roots have an effect? So we have repeated roots of x minus 2, x minus 2. And we have, again, x minus 2, x minus 2. So at 2, again, it bounces off. Here, we have another repeated root, x plus 1, x plus 1. So that's negative 1. And again, it bounces off. So repeated root of 2 bounces off. X-axis. Okay, and how would you describe the range? Well, if it starts off in this quadrant and ends in this quadrant, it goes to positive infinity and goes to negative infinity. Here, we have the opposite. It starts at negative infinity, goes to positive infinity. So it's all reals, which means that there is no global min or maximum. Global min or maximum has to be finite, which means that it's not infinity or negative infinity. One thing that helps examining the shape is to adjust the window. Here I've already adjusted the windows. And so you'll need to zoom in or zoom out. Making conjectures, we can simplify this step. One tip on a calculator, you want to set the domain as negative the absolute value of the constant value and the absolute value of the constant value, where a is the constant term, a naught is the constant term. Okay, so for this one, we have 24. So we would set the domain to negative 24 and positive 24. But you can see that the domain is actually much smaller for the area of interest. We only went to negative 2.5 to about 3. Here, it's negative 12, so we go to negative 12 and positive 12. But we zoom in a bit because we see that the area of interest is between negative 1.5 to 3.5. And it applies here. This one is a special case. You have to factor out the x first. So we're left with x plus 1, x minus 2. So the constant term is actually negative 2. So we would go from negative 2 to positive 2. Okay, you need to be careful when graphing. You won't get functions like this in this course, but in the future you might run across it. So that's why I'm bringing it up. First of all, this is not a polynomial function because these are decimal values. Polynomial functions have to have integer coefficients. So let's bring up the calculator and let's enter this function. So we have x raised to the power of 5 minus 2x raised to the power of 4 minus 6.0001 x raised to the power of 3 plus 8x squared plus 5.0007x minus 5.9994. And we set the window to negative 6, positive 6. So we use the factor property anyways by rounding this off. And then that's an acceptable window, so graph it. Okay, so we look at this and we see that we have 1, 2, 3, 4 roots. Or do we? It looks like it bounces off there. But let's zoom in. still looks like it bounces off. So I'm going to jump to the punchline. I'm going to set the window. So in fact, we actually need to zoom in a lot. So I'm going to set this to 0.95 and 1.05 and negative 0.01 and 0.01. And graph it again. So, in fact, we have 2 zeros here. It's very important to not get caught up in a graphing error. Need to zoom in a lot. So our domain for the window is 0.95, 1.05, and our range is negative 0.01 to 0.01. And this function fully factored actually looks like this: x minus 1.01, x minus 0.99, x minus 3, x plus 2, x plus 1. And that concludes this lesson.